I want to start out by apologizing. I wrote some slides, and then I filled up /tump, and LibreOffice does not cope well with a full /tump, I discovered. So these slides were all done this morning. All right. So I'm here to talk. The title of the talk is about Filesystems and memory reclaim. But really, what this talk is about the challenges of working across subsystems, where you have people who are deeply knowledgeable about file systems, deeply knowledgeable about memory management, but when the two collide, nobody really has the big picture about what's going on, what is the best way to fix a problem. There aren't any file system people in the room, so it turns out I can be as rude as I like about them. Although I have found out that some of them know how to use YouTube, so they might be watching remotely. So I may have to temper that a little bit. In seriousness, one of the most important things we have is the collaboration summit every year. We have the Linux Storage File System Memory Management Summit, where we all get together. And in fact, at the last one, we discussed the problem that I'm going to talk about. We just didn't get any solutions developed. Well, we got solutions developed, and they were all wrong. So anyway, I'll be talking about in a bit. So to the specifics of this case, you're probably going to want to know a bit about what memory reclaim is. Usually, you call kmalloc, the slab allocator gives you some memory, and it's all good. But sometimes the slab allocator doesn't have any memory to give you, so it goes off and it asks the page allocator, and the page allocator usually has some memory it can give you. Sometimes it doesn't, and then it goes off and has to actually try and get some memory from elsewhere in the system. So most places allocate memory, either allocate it for like the whole time that the machine is booted, or they'll allocate it for a very short time and then they'll give it back again. But there is a third category, which is caches. And as I think we all know, the larger a cache is, generally the better that the thing performs. But of course, that's just that specific system, right? It may not be the case that the whole system performs better if all of your memory is in the d-entry cache. So there's a mechanism to tell caches, hey, we're low on memory. Can you prune your cache a bit? Can you give us back some memory? And I'm not going to go into the details of exactly how that works, because that's not important for this talk. So that's done by registering what's called a shrinker. And we're going to be talking about shrinkers a bit. The other thing that's important to know is that Linux can call shrinkers both directly, that is, when you've tried to allocate some memory, and it's failed, so you go and try and call the shrinkers directly yourself. I mean, the system does it on your behalf, like you don't have to write out the code to do it, but it's your process. You've called kmalloc, you get to run the shrinkers because you want memory, so it seems kind of fair that you should have to pay the cost of reclaiming it. But some parts of the kernel aren't able to do that, right? If you're in interrupt context, you can't go calling into bits of the kernel that don't expect to be called in interrupt context. And for those cases, we have something called kswapd, or as I've called it in these slides, I've tried to use this terminology throughout, in the background. So there's a background thread, a kernel daemon, that goes around and tries to keep memory consumption within safe levels. Ideally, you'd never have to use this, but for things like a router, where it's doing most of its allocations in interrupt context, there needs to be something that's running at user level that can do this background freeing for you. All right. So why do file systems have problems with memory reclaim? Because file systems are complicated. Oh, I'm sorry, there's something I forgot to mention on the previous slide. I gave an example of 3 different caches there. The D-entry cache and the inode cache, these are slabs, right? They are they use the slab allocator, they have their own caches. But then the slab allocator itself is also a cache. The slab allocator keeps around completely free pages that it could return to the page allocator for reasons of performance. Right, Vice Mill? He's nodding, that's good. All right, I didn't completely misunderstand that part of how it works. So, yeah, so slab itself has a shrinker, and then some of the slab users have their own shrinker. So there's a D-entry shrinker, and there's an inode shrinker. All right. So, it can be complicated to free an inode or a D-entry. And lots of other things in file systems are also complicated because file systems are insanely complicated things to write. And this is an example that we already solved, right? You take a lock inside the file system. You take a lock. Then you try to allocate some memory. Oh, we don't have any. Okay, we'll go into reclaim, and then reclaim says, oh, well, I'll try and free some memory from your file system. And that needs to take the same lock. That's a pretty easy one for LockDep to be able to handle. LockDep will tell you, hey, you took this lock, and then you entered reclaim. And actually, LockDep can catch this before it happens, because as soon as anyone enters reclaim, it records that there's a dependency between being in reclaim context and taking this lock. So it knows that the lock must be taken within the reclaim context. And then, later on, in a completely different thread, you take this lock, and then you try and do something which might enter reclaim, and LockDep says, hang on a minute. It may or may not be a problem this time, but at some point in the future, there is a theoretical path that gets us to having this double acquisition problem. And obviously, this is a very simple example. And it has a simple solution. We have this NoFS concept that says, hey, when you allocate memory, just don't enter any file system. So even though we've got a lock which is local to my file system, just don't enter any file system. And that probably seems overly restrictive to some of you. It certainly did to me when I first heard about it. It's like, well, why don't we have like a bitmap that says, well, this is an ext4 lock, but we haven't tried entering XF, but that shouldn't prevent us from entering XFS. And then somebody said, yeah, what about stack depth? Because generally when you're inside a file system, you've got a fairly deep call chain already. And so to go into direct reclaim, you're going into another potentially quite deep call chain. And we can fall off the bottom of the kernel stack, and that's not a good thing. I said, okay, I'm not going to try fixing this problem. Yeah, I think that's everything I wanted to say. All right, so in March this year, we got 3 bug reports in quick succession. This wasn't entirely a coincidence. You can see from the URLs that the first 2 are very, very similar, and they're actually submitted by the same person, who is running syscaller. They're in the class of people who has taken syscaller. For those of you who don't know, syscaller is a product from Google. Not a product. It's a tool that Google have developed to really stress the Linux kernel. And it's really good. It finds so many problems. So many problems that we had to sit down with the syscaller developers and said, you're killing us. We can't fix all of these bugs as fast as you find them. Either you need to put a lot more people onto fixing these problems, or you need to slow down how fast you're submitting them, or something, because there's so much noise right now. And they did that. And so now we have this lovely website where Syzbot puts up all of the known bugs. So they've automated a whole bunch of this, right? So it doesn't overwhelm us. It doesn't. It keeps track of when bugs are inadvertently fixed. Like, you don't have to tell it you fixed a bug. It will just say, "Oh yeah, I noticed this one doesn't reproduce anymore." And it does all kinds of other cool things, right? It does bisects for you, and it'll often finger the exact patch that caused the problem. Yes, sometimes it goes wrong. I mean, it's software. Bugs are fickle and sometimes hard to reproduce. And I mean, I think the experienced kernel developers in the room probably all know all of this, because some of us have done it all by hand. But hey, Syzbot is automating this, and that's really, really cool. Where I have a problem are the independent security researchers who tweak syscaller somehow, run it manually, and then inundate us with bug reports because they've brought back the original problem. And what I really want is for them to work with the syscaller upstream and get their changes into syscaller, and then let Syzbot handle all of the stuff that it's really good at doing. I'm not saying I want to replace them with a small shell script. I am saying that I want them to take advantage of the automation that already exists instead of coming up with these boutique bug reports. But importantly, because I would have just blown this off, frankly, importantly, the third bug report was from a real human being who I've actually met and is a long-time kernel contributor, not particularly in the file system or area, but clearly in their day job, they managed to create a scenario that hit basically this same bug, and we recognized it as being a variant of this other one. And that was a coincidence. The first two, not a coincidence. Like, this security researcher has done something and repeated the problem 2 times. But the third one, human being. And so looking at that was kind of interesting, because both ext4 and FAT were implicated, and both direct and background reclaim were implicated. So that's kind of interesting. This is a somewhat sanitized stack trace. I trimmed out a lot of the unnecessary functions so I could blow this slide up, so I hope those of you at the back can see this. And we read it bottom to top. Well, you see we've hit a warning. And that's what got the security researcher interested. Because when you hit a warning, maybe that's a security bug. They said it was a security bug. It's not a security bug at all. But it is a bug, and it does need fixing, and it's interesting. So we're going to talk about it. I won't dive into exactly what the warning is about at this point. I'm going to explain to you what's going on in the system at this time. So we start out at the bottom, PTE alloc1. We're allocating a page table. We've taken a page fault, and we need to allocate somewhere to put the page table entry that is going to resolve the page fault. All right, so we call the page allocator. Page allocator doesn't have any memory, so it says perform reclaim. We try to free pages. We call the slab shrinkers. That calls into super cache scan. So each file, a super block is a mounted file system. So there is a list of each super block in the system. So each mounted file system in the system. Okay, so now we're going to prune the iCache, the inode cache. We're going to evict an inode. Okay. Turns out this is a FAT. That's the DOS. I mean, it doesn't really matter which file system it is. As I said, one of the other stack traces implicates ext4. I just chose this one more or less at random. All right. So we're going to throw away a FAT inode. Well, it turns out this inode has some blocks on disk allocated to it that are beyond the end of file. This happens for a bunch of reasons, right? Maybe it was in memory, like we we did something to this file, and then we said, oh, let's just shrink this file a bit using the truncate syscall. That happens, that's one reason. Some file systems will allocate beyond the end of file in a speculative way because they think you're going to keep appending to the file. However it happened, doesn't really matter. The point is that we have some blocks allocated to this file that are beyond its current end of file. So if we were to just throw this inode away without freeing them, we would have a leak on disk. So we have to now free these blocks. So we call flat truncate blocks. Makes sense. And then we discover that we don't have the block bitmap in memory. So we need to go and read the block bitmap from disk into memory so that we can clear the bits that say these blocks are in use, and then we can write it back. Oh, okay. So we need to read it into memory. That means we need to allocate some memory, and we end up back in alloc pages slow path, which is where we started. Without even knowing what this warning's about, I think we can see the problem, that we're trying to allocate memory in order to allocate memory. Not good. So I didn't quite analyze it like this at first. I started looking at, well, what's the warning, right? Because what's the warning is generally what gets you the answer you're looking for. So we've told the memory allocator it is not allowed to fail. We've told it there is no circumstance under which failure is an option. You must try forever. But we've also told it, hey, we're in reclaim. And we told it in perform reclaim, which was like the very next thing we did after going into alloc pages slow path, right? And then we used GFP no fail and SBB read. That's fine, I've no problem with that. Both of these things are reasonable to do. But you can't do both of them, right? Just because, like, when you're freeing memory, you can't allocate more memory, generally. All right, well, how are we going to fix this? I'd like to thank everyone at LSFMM and indeed on the EXT4 weekly phone call for coming up with some of these suggestions. These weren't all my ideas. We've investigated all of them, and none of them work. So the first is, well, okay, so let's suppose we do need to allocate memory in order to free memory. But then we had the people who care about supporting drives that have like 16K sector sizes were in the room, and they were like, is that going to be okay? And the memory management people looked unhappy and said no. Okay, so that one's out. I think it was Vlastimil suggested that we use mempools to reserve enough memory. And then the file system people said, sorry, we can't know ahead of time how much we might need an unbounded amount of memory. Okay. Well, if we don't know like generally how much we're going to need, could we know specifically what we'll need for any given inode? Again, no. And then the file system people said, and by the way, we might need to run a transaction. Clearly not, FAT does not have transactions, but other file systems like ext4 do. And it became pretty clear that trying to do all of this in the evict inode path as part of reclaim was not going to work. All right. Well, what if we only allow inode reclaim from background context? At the time, we hadn't quite figured out that, hang on a minute, one of these is from background context, so clearly that doesn't work. But the thinking was, maybe it's like we're just too deep in it, and perhaps if we just like ask kswapd to do it, and no, like you're kicking the problem to the wrong place. All right. Well, if we're trying to evict an inode, and it turns out we'll allocate memory, how about we just have evict inode fail? Right now, the evict inode method it returns void. What if we just made that return int, and then we could allow it to fail and like put the inode back on the list and choose not to evict it? And the file system said no, can't do that. There's parts of the kernel that rely on once you've started to evict that you finish. All right. I'll come back to that one. So the XFS people, and by that I mostly mean Dave Chitner, but Derek Wong had some thoughts about this too, is that XFS doesn't have this problem. We could convert the entire Linux VFS to have the same inode lifetime rules that XFS does, and then we wouldn't have this problem. Have you been to a fairground and they say, you must be this tall to get on the roller coaster? I'm not tall enough to do that. I'm not tall enough to get on that ride. But I thought, you know what I could do? I could just punt it to a work queue. I could say, no, we can pretend to kswapd or to memory reclaim. Yeah, we've freed that inode, but not actually do the work of freeing the inode. We defer the work of freeing the inode to later. So I sent that patch out about 3 hours ago. And Jan Kara very kindly told me I didn't know what I was talking about, which is true, and he was very nice about it, because Jan Kara is a nice guy. So, kind of going back to this idea now. Maybe we can just say, hey, if it's clean, perhaps that's an easy thing to evict. Whereas a dirty one might have these problems like, oh, there's blocks after EOF and blah, blah, blah. But a clean inode, we should just be able to throw away because there shouldn't be any problems with it. Like, it's clean, we haven't modified it. Why would we need to run a transaction if we haven't modified it? Or if we did modify it, we cleaned it earlier, and presumably we ran a transaction at that time, or we freed blocks at that time. So I'm kind of interested in doing this one. I'll take a look at it. I literally saw Jan's email 10 minutes before my talk started, so I haven't fully digested all the myriad ways in which I am wrong. So, honestly, I mean, this has been kicking around since March. We talked about it in LSFMM in, was it May, April? April, I think. And really nobody's done any work on this. And so I thought, well, if I submit a talk to Kernel Recipes, that's going to force me to write some code. And it almost worked. I mean, I started writing the code like a week ago when I panicked and realized I hadn't done anything for it. So it's certainly, lit a fire under me. I've been busy with, other projects. So we've all got other projects. This is a fairly low priority bug. Matt, who is the human being who has it, said, this isn't a high priority for me to fix. It's just something I thought you'd be interested in seeing. And, I mean, somebody who's running syscall doesn't really care if the bug gets fixed or not. You might get some poor statistics next time somebody does a statistics run, but, eh. How are we doing for time? I've got like 5 minutes before to take questions, I think. So perhaps I'll just go through, we've had disagreements between file systems and memory management over the years. But I do think it's led us to better solutions on the whole. For example, it used to be that in Reclaim, putting aside inode caches and D caches, most of your memory is actually tied up in the page cache. And so what used to happen is, and I think Vlastimil touched on this a little bit in his talk earlier, is that we used to write back, if we found a page that wasn't particularly in use, but it was dirty, we would write it back during Reclaim. And the file system people weren't terribly happy with that, because this makes sense for anonymous memory. If you've called malloc up in user space and you've got a bunch of data in user space, generally it doesn't get swapped out. Usually either the process exits or you call free before you need to swap out that memory. So it very much makes sense to defer writing out anonymous memory until you actually need to. But file systems are different. If you have dirty memory in the page cache, either from having called write or having mapped it and stored to it, you want that file to be up to date. Like, if you get a power cut, you probably want not to lose too much work. I mean, I think, maybe losing the last 20 seconds of work is fine, but losing the last 8 hours of work, you'd be angry, right? I mean, the same way that I was angry when I lost my slides, right? Some of you were on IRC and saw my reaction live. That was great. So what file systems do is they actually write back way earlier. There's write back going on basically all the time. It's looking for dirty inodes, and this is kind of important, when you see when you find a file, you write back all of the dirty pages in the file in ascending order, because that gives you a really nice I/O pattern. And I know that we have I/O elevators and so on that try and create a nice I/O pattern that's putting everything in the right order. But it works better if you start with the right order and then the I/O elevators just scan it and say, oh, yep, that's good, thanks. Nothing to do here. It's just quicker. And it helps the file system lay out files on disk better. It's just better to do this like an entire inode at a time. Because if you let the memory management system do it, you get it in the order that it's on the LRU list. So it's the most recently dirtied page will get written back first. And that's not necessarily, you didn't necessarily write that file start to end. You might have written a bit here, a bit here, a bit there, a bit in the middle. And that's not the order you want it written back in as the file system, or indeed as the user. You want the whole file written back in order, because that's going to give you better I/O bandwidth. For those still using hard disks, it's fewer seeks, but it's just better for all of you. I've got time for a couple more. Any requests for one of these I should talk about? No? Okay. I'll just do the next one. Kmalloc. Right, so when file systems want to do I/O to a kernel address, it's kind of like doing direct I/O to user space. We have to satisfy the alignment constraints that the underlying device is willing to DMA to. And those vary by I/O device. Like NVMe is happy to do 4-byte alignment. I know because I wrote that in the spec. But if you ask it to do something that's only... yes, Paul?
This is for memory that's 512 bytes and larger, correct?
Paul is asking, is this for memory that's 512 bytes and larger? Yes, yes it is. Yeah. If you're allocating 8 bytes, we don't force an 8 byte to 512 byte alignment. That would be quite the waste of memory. Yeah, so if the file system allocates 512 bytes in order to read one sector from your hard drive, at least for ODirect, we require that it be 512 byte aligned, because that definitely works for all storage hardware that is known to exist. Again, it would be kind of weird to have like a 4K alignment, but only a 512 byte size. That hardware isn't going to get off the drawing board. Somebody's going to say, hang on a minute. But Slab was not willing to make that guarantee, because you might ask Slab, can you put what's called a red zone between objects? And a red zone catches overruns. So if you want to put a red zone between objects and you want the objects to be 512 bytes in size, now your red zone also has to be a minimum of 512 bytes in size, which is generally considered to be far too high. But given the choice, given that if you don't have the 512 byte alignment rule, what the file system actually has to do is allocate a kilobyte and then find a 512 byte aligned chunk within that kilobyte. And that's just as bad, really. So there was a bit of discussion, mostly friendly, and we ended up with satisfying what the file system people wanted, which is that every size above or equal to 512 is now definitely going to be 512 byte aligned. And that's a good thing. All right. I've reached question time. So if I don't get any questions, I'll just keep going with this list, but I'm happy to take questions. Blastamel? Can somebody grab the speaker box?
So a clarification, we align power of 2 sizes to power of 2, and if it's not power of 2, we don't care. So that's more correct. But for 5012, it's the same.
Okay, thank you for the clarification.
And the blocker actually wasn't the red zone, like, deciding to adjust red zone to just waste more memory wasn't a problem because you are debugging, so you pay the price. The problem was the slop allocator couldn't guarantee that, so only after it was removed, it was possible to start guaranteeing that.
Thank you for removing that dreadful old allocator. I really appreciate that. Removing that allocator helped with several different things that we couldn't do before, but we can do now. For example, RCU can now free any object, any slab object, whether it's been k-malloced or came from a slab. So that was just beneficial for everybody because it let us get rid of a whole bunch of silly little functions that just said, oh yeah, go free this object in a special way rather than go free it in the normal way.
But I have a question for your suggestions. So the evicting only clean inodes, right?
Yeah.
But sometimes we will have to evict the dirty ones as well, and so that would be not from PF memmalloc, so it would be in kswapd. But you said the reports also implicated kswapd, so what was the issue there?
Okay, so PF memmalloc is set both by kswapd and by direct reclaim. Okay. We would evict dirty inodes at superblock unmount time. This code path is shared between superblock unmount and the slab shrinker.
So would they accumulate until we unmount? Would that be Wouldn't that be a problem?
There are other mechanisms that clean dirty inodes. Okay. Like I was talking about the write back earlier, that we would clean the inodes at that point.
Is GFP no-fail evil?
I would say that GFP no-fail is a necessary evil. We added GFP no-fail relatively recently, maybe 10 years ago, because the alternative is that generally file systems, not just file systems, but generally file systems, implement their own retry loop. And it's much better to have a small amount of evil in one place than it is to have the evil spread evenly throughout the kernel. There are some places that just genuinely can't survive, right? You need to allocate memory, and like there's no point in having an error return because there's nobody to see the error and everything's just going to fall apart. It is sometimes used by lazy people who really ought to check their errors. That is sad. But it's better to have that abuse than it is to have the open-coded abuse that we had before. So by all means, question everywhere that you see GFP no-fail, but be aware that there may actually be really good reasons for it, and this is the best that any of us have been able to think of. Lorenzo?
I was wondering if, similar to the effort that was made years ago to limit the maximum stack depth, it wouldn't be possible, to some extent, to try to limit the maximum allocation that is done in a call stack and spread the effort on everyone, and consider that during certain phases like this, we can use some emergency areas which are used only for this and try to reduce them over time.
Yeah, that's a reasonable suggestion. I don't think it's going to help this case. So it turns out that what all these three cases have in common, and I snipped it out of the slide for clarity, is that they're all running in really tightly constrained C groups. So they are artificially limited, and basically this is the only way you can create these kinds of failures where you've actually lost the you no longer have all your file system metadata in memory, because file system metadata actually gets used fairly often and it stays in cache generally because it stays fairly hot, but like you can get it evicted if you try hard enough. So we might actually see this kind of thing coming up more often, just because people don't like to pay more money to their cloud provider, so they tend to keep their jobs fairly tightly constrained. I don't. So the problem really is that the whole system is tight on memory, rather than that this particular call chain has allocated a lot of memory itself.
So I have a kind of a follow-up to the comment that you made that we might be seeing more of these issues pop up. So do you, have you seen before, or can you envision other subsystems where this reentrancy problem may occur? So from what I understand, this is fundamentally a reentrancy issue. You go from the file system to the allocator, and the allocator goes back into the file system. So are there other subsystems that could interact with the MM subsystem in this way? Or do you have any, yeah?
Well, actually, this one isn't file system to memory allocator back to file system. This example here was file system to memory allocator back to file system. But this one is page fault handler into file system. So the file system is only involved once here. Fundamentally, this is, I'm trying to allocate memory in order to free memory in order to allocate memory. So yeah, I mean, in theory, any shrinker could have this kind of problem. Most shrinkers are not as complicated as file system shrinkers. Most shrinkers just say, oh, yeah, let me just free some stuff. I mean, if you look at calls to register shrinker in the kernel, you can find, there's like 100 of them. Just choose one and look at it, and it's going to be simpler than a file system one.
Thank you.
So you mentioned this stack trace, but what actually happened when this stack trace got emitted? Like, did the process get killed? Did the system fail? What?
Okay, so when you run syscaller, you set the flag call panic on warn. So the system panicked because it had been told to, because that's the best way of getting a usable dump out of it. If it hadn't been set, I believe this code path would continue and use its best efforts to actually allocate memory to free memory to allocate memory. Whether it would succeed would depend on how successful reclaim had been prior to getting to this point. Because when we do reclaim, we apply pressure to each slab in turn and indeed to the page cache. So we may already have freed up memory and then succeed in this path of allocating memory to free memory to allocate memory. But I can't promise that. So it is right that we have this warning here. This really is the canary that tells us, hang on a minute, we've made some horrible mistakes. The system would probably survive this. But it's unsightly. It is a bug. It does deserve to be fixed.
Okay, thank you.
Matthew, isn't this even worse, like with stacked devices, stacked block devices, or even Fuse, LVM, software RAID, and whatnot?
Yeah. I mean, we can construct a deeper stack than this for sure. I mean, the stack depth isn't really the problem here. Yeah, like you say, you know, if we're doing something with Fuse or with a network block device or something like that, there are other places where we might need to allocate memory. They generally don't use GFP no fail, so they're not going to get caught by this warning. But I don't know, like if you're running, let's say, FAT over a network block device and the network doesn't manage to send the command because it can't allocate any memory to send the command.
Because I remember a long time ago there was a big discussion about, you know, swapping over, you know, a file on a network file system. That's kind of crazy, but, you know, it can happen.
Let me give you another one, swapping over iSCSI. There are people who want to do it. I mean, it's swapping over iSCSI is actually a bit more likely to succeed than this is, because this is an unbounded amount of memory, whereas something like swapping over iSCSI, we can put a fairly tight bound on how much memory we will need and make sure we've set that amount of memory aside. And so we will actually make progress in freeing memory, whereas evicting an inode like this is going to potentially take an unbounded amount of extra memory. And at the end of the day, we've freed one inode. We may not even have freed a page. We've just applied the bit of pressure to the inode cache. We've freed one inode and taken so much effort to do it.
Yeah, thanks.
So you mentioned that one of the fixes is putting that under a worker that's going to run under a K-thread, right? Is a dedicated K-thread, does it make any sense? Or maybe even have the file system be told that, hey, I need you to evict inodes. You must have your own K-thread to do it. And each file system would have its own K-thread.
Yeah, maybe. I mean, that might work, and it might also be too complicated, because this is a rare situation. So Yankara explained to me, and I haven't fully understood this yet, that generally we don't come down this path. That in order to come down this route, we've actually lost a race. Usually the Dcache has the last reference to an inode, but somehow somebody else had a temporary reference to the inode, and then the Dcache one got put, so the Dcache wasn't the last person to put it, and then it went away, and then we found it, and we're trying to evict it here. It doesn't entirely make sense to me, but Jan does know this area significantly better than I do, so I'm trying to understand why he's right rather than trying to find a hole in his explanation.
Yeah, I'm trying to connect to the other thing that you mentioned, that the file system is in a better place to pick which inodes to evict in which order. So maybe this would just like be a signal, hey, I'm under reclaim here, can it be a little bit more aggressive?
Yeah. Yeah, I think that's true.
Last one?
Can you go back to the stack? So it seems to me that you get to try to free pages, and then when you get to evict, Yoda steps in and says there is no try. And so doesn't that mean then that the only solution to this is your suggestion to only evict clean pages because of the semantics, unless you want to change evict? You can't ever use evict in a try context because there is no try.
Yeah. Yeah, I think we have to stop before we get to evict.
Yeah.
We have to say.
So either prune iCache SB can figure out that the file system doesn't actually have enough information to decide whether it can evict, but then there's a time of check to time of use problem, or you just say, I'll give up here and hope that there's another shrinker that can save me.
We do know at this point that the inode ref count is 0, so nobody else should be able to make the inode dirty. Like we're holding the ilock, I think, if I remember this code correctly.
Could you have both infallible and fallible eviction? And then use the fallible one in reclaim and the infallible one in whatever case they need infallibility?
No, because by the time we're asking the files, we did actually talk about that as one of the variants, but the problem is that by the time we're calling the file system, we've taken the inode off at least one list. It may still be findable in other ways, but we've taken it off at least one list, and apparently you can't put it back on that list once you've taken it off. I don't really understand this part of the BFS well enough to make a declarative answer, but it was discussed and it was rejected.
Tricky stuff.
Thank you.